All right, let's talk about what happens when things don't work out so well for our power series solutions. So when you're doing a power series, right, you're doing a Taylor series expansion about some number, right? We're assuming that the solution can be written as a power series. Now remember how power series is constructed with derivatives, which means the function is differentiable. If your function is differentiable, you're assuming continuity. So what happens when our assumptions break down? So first, let's recall what we did say. We assumed P, Q, and R were polynomials, and polynomials are continuous with no repeated factors. And I gave you some vocabulary saying that if you plug in a certain value of x, which you are going to use in the polynomial, in the series expansion, right, as the center. If there are x's that if there are no x's that make this first polynomial equal to 0, we can go on with our business, right? X of 0 is the center, right? We're assuming that we have y equals this polynomial, infinite polynomial that was built by Taylor, so it has derivatives and continuous, right? Everybody's a polynomial. We're also happy, right? Everything's cool. And then we just constructed our power series solution, and the algebra could get a little messy, yada, yada, yada. And I told you, however, that if there is a certain x that you plug in for the coefficient function of y double prime and you get 0, firstly, where did y double prime go, right? What the heck? And we call that not an ordinary point, but we call it a singular point. And if we have a singular point, we need a different method to solve this. And we're not going to get into the different method yet in this video, different methods in this video, but we're going to talk about identifying the singular points versus the ordinary points. So first I need to tell you that this form of the differential equation is not standard. Standard form of a differential equation, second order differential equation, has that coefficient of y equal to 1. So you've got to divide off that function. And now hopefully you can see here why plugging in a number into p and equaling 0 is a bit of a dagger. That whole continuity issue goes away, right? If I plug a number into these denominators and create 0, I've got problems. Those are my issues. So if the function in front of y double prime has no x's that create 0, you've got no issues. Every x is an ordinary point. Build your power series about whatever center you want. However, if you have any values of x that do create 0, you need to find those x's, and those are called singular points. So we need to know what x's can't we use to construct our power series solution. Analytic is another vocabulary word, and analytic just means I can construct a Taylor series. If I can construct a Taylor series, it means there's no issues, right? So we have a lot of analytic functions from calculus. Sine, cosine, e are certainly our polynomials. Every center that you could pick is an ordinary point. They're analytic because at any x, I can construct a Taylor series. So again, we've assumed the solution to this second order differential equation with functions in front of our y prime, and y's is a power series expansion about this center, and that this solution behaves similarly to the function in front of y prime around that center. But what happens when I plug in 0 and I do get 0? Obviously, there is an issue at 0, but what about, remember, we're talking about behaving similarly to this function p around the center. So I know that if plugging in x sub 0 gives 0, at the center I have an issue. But what about around the center? What about as I get close to the center? Firstly, you need to know that whatever x does create 0 in p of x, that value is not ordinary. The function is not analytical there at that point. So what does that mean? If I plug in any x and I don't get 0, I say I'm analytic there. If I plug in an x and I get 0, I am not analytic there. If you are analytic, the point is ordinary, no issues. If it is singular, issues. So I keep saying issues. What do I mean by issues? Right? How bad is my issue? So let's talk about what issues we could mean. If everything is swell, not only at x sub 0, but at any point around x sub 0, my solution behaves, right? The behavior of my solution around x sub 0 behaves a lot like p of x. So what happens if p of x, though, at x sub 0 doesn't exist? I have an issue. Or not doesn't exist, I just have issues. What does that mean? Well, it could mean something heinous, like the behavior looks like this around there. Ugh. Or it means this. Ugh. Those are devastating issues, right? No issues means everything's fine. Issues, I've got two bad ones. So when I say how bad is it, those two are really bad. How about some functions? How about some issues that may not be as bad? Around x sub 0, what if I have maybe I do have, right, an absolute discontinuity, but the behavior around there is calm in the area around that issue at x sub 0. Or what if I have an issue like this? I've got continuity, but not differentiability, but everybody's calm everywhere else around it. I don't have this horrific jump, and I don't have this infinite discontinuity. If my singular point, right, so first I have to identify a singular point, right? Again, if I plug in and I don't get 0, x sub 0 is ordinary. But if I plug in x sub 0 and I get 0 into the leading coefficient function, how bad is my issue? X sub 0 is singular, x sub 0 is singular, x sub 0 is singular. This is an awful singularity. Awful. These are called irregular singular points. These singularities are weak. They're not that bad, right? They're weak singularities. I just can really, and in a differential equation, what the solutions look like around here can be very interesting. We call these regular singular points. If I have regular singular points, I have hopes that there are some other methods that will help me get a solution to the differential equation, even though I have these singular points. Okay? Even though I have them, I don't have hope up here. I don't have hope. So the limit. Here's how I deal with how bad is it. How do I tell the difference between, I figure out how I get singular, right? What makes, I set P of X equal to 0 and solve for X. But then if I want to know, are my singular points irregular or regular? In other words, who can I have hope for and move on? It can be proved, and no, we are not going to prove it, that if you take a limit of these two ratios after you've gotten the differential equation in standard form, and you've done a limit of the factor x minus x sub 0, right? That's the singular point. Times the ratio in front of y prime, and you take the limit as x approaches that bad x, your singular point here, squared times the ratio in front of y prime, in front of y. This isn't from y prime, this is from y. If you evaluate those limits and neither limit is an infinity, then you have some hope. Then your singular point is regular, and we can try to apply some other methods to solve the differential equation. So, for example, if I ask you to find all singular points and determine whether, why didn't I do a space there? Each one is regular or irregular. Here's my differential equation. I identify my P, and I say to myself, x equals 0 is an issue. Then I get in standard form and simplify. So do you see why I divided by 2x squared here, but this x canceled out? Now I'm going to identify the q over p. And your book calls that little p. And identify this function r in front of y divided by the function p. Your book calls that q of x. And I'm going to evaluate their limits. Take my singular point, because honestly, right, this is really 2 times x minus 0, and this is really 2 times x minus 0 squared. So I'm going to take the limit as x approaches x sub 0 of x minus my singular point to the first times p of x. So fill in x sub 0 here, here, and fill in little p of x there. So that's the limit as x approaches my singular point, x minus my singular point to the first power. What is that limit? Right? When this, of course, is just this part simplifies to negative x over 2x. What is that limit? Powers are the same. Limit is negative 1/2. When you're doing, remember, that's for y prime. When you're doing the limit with the function in front of, or the ratio in front of y, you have to have the squared, right? Again, that just comes from a proof. So replace again your singular point here, here. And what does this look like when you clean it up? Well, that's x squared times x minus 5 over 2x squared. The x squareds go away. So that's what, 1/2 x minus 5/2. What is the limit as x approaches 0? Plug in 0 and you get negative 5/2. Both limits, and it does take both limits are finite. They're a finite number. Neither one of them is an infinity. Since both of them are finite, then the singular point that I already knew I had, I already knew it was singular. Now I know it is regular. And if it's regular, I have some hope of being able to find a solution despite the issue at zero, because I want to actually find us, right? I'm going to think about what's going on really, really close to zero. So that's great, but I prefer not to have to take a limit each time. I do have a shortcut. You're welcome. So first, you're going to still find the values of x that make the coefficient of y prime equal to 0. You know you have issues there. If you're asked if they are regular or irregular, issues, and again, remember, we call that singular. Are they regular singular or irregular singular? Our steps are just like before. Get it into standard, sometimes called normal form. There's the two ratios, the one in front of y prime, the one in front of y. Some will call this P of x and Q of x. Again, I think your book does. Remember, every other x is an ordinary point and means the solution is analytic. Everything's nice. I can use my Taylor series, right, and then construct a power series solution around that x sub 0. I don't know why I made that step 2, right? That should have just kind of been a note. Anyway, find your x sub 0 that create 0 in the denominators now. But really, you've done that up here. If you just look at this and say set it equal to 0, you really have done step 3, right? Create 0 in the denominators of little p and little q. Those are your singular points. They are the same x's that make the coefficient of y prime before you got into standard form equal to 0. Every one of those points is singular, but that's either regular, have hope, or irregular, hopes dashed. So simplify your ratios, right, to make sure that there are those no repeated factors in either ratio. Then determine that power for each x minus your singular point in your denominator. And then look at that power. This is, again, not the limit, right? Remember, the limit of y prime was x minus 0 to the first, and the limit involving just y was x minus the center squared, or that singular point squared, right? So just look at the denominators of your little p and little q after you've simplified the ratio, and look for your x minus your singular points. If in the denominator in front of y prime, that power is less than or equal to 1, and that same factor in the denominator of the second ratio, little q, if the power on that factor is less than or equal to 2, then your singular point is regular, otherwise it's irregular. So that sounds kind of gross, and when I was typing it up, I was like, oh, you know what? These steps sound worse than the actual process. But let's do example 1 again. So here's my equation. I identify 2x squared as p of x, capital P of x. You can either think your irregular points here, singular, or you can wait till you get this into standard form. And now just look at P of x and Q of x. And again, if you want to make sure. Look at the factors of, this is my singular point, so look for x minus 0 in denominators after you're in standard form. And look at those coefficients. In the coefficient of y prime, the power n needs to be less than or equal to 1. Is it? Check. And in the coefficient of y, the power of x minus your singular point needs to be less than or equal to 2. Is it? Check. Therefore, is singular but regular. So I have hope. Hope springs eternal. I think maybe I did that right? I knew it was singular. I forgot I typed all this out sometimes. I looked at the denominator, saw a power of 1. That again is of y prime. Looked at the denominator of y, saw that it was a 2 or less. Therefore, it's a regular single point or a single regular, singular, regular. I don't know what's, and again, that's good. Yay. I mean, I wish I didn't have any issues, but if I have an issue, I would rather it be regular. So let's try another example. Maybe you pause the video and try this. This one was a little more complicated because look at the function in front of y double prime. That's my p of x. So to get it in standard form, divide everybody by 2 times x minus 2 squared times x. 2 times x minus 2 squared times x. And of course, you're doing it over here, but just dividing by 0. This is in front of y prime. This is in front of y. That looks like a first, but it's a prime. So notice your singular points, which you could have done up here. What makes p of x equal to 0? Or you could do it as it's in the denominator, right? When it's in the denominator, it'd be the same thing. Your singular points are 2 and what? And 0, right? So you've got 2 singular points to classify. So let's clean up, right? This one we call little p. This one we call little q. So let's clean that up. P 3 over 2 times x minus 2 squared. What does the power on x minus 2 have to be? This has to be, n has to be less than or equal to 1. Fail. Don't bother to check that one. Therefore, irregular, I don't have any hope. For that one. Since it's an and situation, I don't bother and go check Q. But I don't just have X to check, right? That was me checking 2. What about checking 0? Right? There really is an x minus 0 down here with a power of 0, right? Is n less than or equal to 1? Check. Whoops, I wrote 0 and I meant 2 here. Therefore, x sub 0 is equal to 0. You can't make that conclusion right now, can you? I have a check, so I need to look at also Q. So I'm not bothering to check. It doesn't matter that these two cancel out in Q. This doesn't matter, right? 2 was already a fail over here. But what about 0, right? The x didn't cancel out, but what power is it? And for Q, the power on x needs to be less than or equal to 2. Check. 2 checks for x sub 0 equals 0. Therefore, a regular point. Let's do another one. Right. What makes p of x equal to 0? Right? And when you divide through, so you have 2 singular points to check. So to check them, I look at p for -3, and I look at x minus 3 to the n in the denominator. X minus 3 is to the first. N is less than or equal to 1. Check. And what else do I have to check? It's little p. Little q. X minus 3 is to the what? Also to the 1, but for n just has to be less than or equal to 2. Check. Therefore, x sub 0 is equal to negative, is singular, but it is regular. Yay. How about 3? Right? Do you see how much faster this is than doing a limit, right? Same situation. X minus 3 is to the first. Whoops, I'm sorry. In P, x plus 3 is into the 0, but n has to be less than or equal to 1, so check. In Q, I do have x minus 3 to the first. Oh. I'm such a silly person. That was positive 3. This was negative 3, right? So x minus 3's to the first and to the first there. Negative 3 would make this x plus 3 and this x plus 3. X plus 3 was to the 0 in the coefficient of y prime. In the coefficient of y, x plus 3 was to the first, but n, the restrictions are n has to be less than or equal to 2. Check. Therefore, x sub 0 being equal to negative 3 is singular because it made p of x equal to 0, capital P of x equal to 0, but is regular, right? So a little bit of a shortcut to that limit work. All right, we will do some more practice of that. Your homework for this should go real quickly, and we'll do some more practice and go on to what are the methods we can use when we have a regular singular point. All right, see you in our next live session.